and we're doing the second part of Chapter 2 of the Hanna book. And we're just covering the binomial distribution, which is the discrete distribution, and the normal distribution, which is a continuous distribution. And when you do the homework problems, there's a video on binomial, on doing a binomial problem using Excel and using the full functionality of Excel to calculate the probability density function, which is the probability of a specific number, or the cumulative density function, which is the probability of getting r less than or equal to a specific number. And in the normal distribution, we use the norm.dist functionality in Excel to do all our calculations there, and we only have the cumulative distribution function because the probability density function returns an answer of 0 for a specific value of the random variable x. The cumulative density function is a probability of x being less than or equal to a certain number. So cumulative is what you would use in continuous random variables only. In discrete random variables, we look at both the probability density and the cumulative distribution functions. So the binomial distribution, which is a discrete distribution, is based on the Bernoulli process. From a couple hundred years ago, the Bernoulli brothers were famous mathematicians and economists in Switzerland, I believe. And the Bernoulli process is, on which the binomial distribution is based, has the following assumptions or underlying behavior that must be met for the binomial distribution to be applied. There are a fixed number of trials. I'm going to flip a coin 10 times. I am going to inspect 20 items to see if they're good or defective. Each of these trials, each item in the trial, each coin toss, each product that you're expecting for quality has only two possible outcomes. For coin, it's a head or a tail. For a quality inspection, it's we're interested in the failure rate, so it's the number of failures. Each item that you look at has either is a good product or a defective product. The probability of each outcome stays the same from one trial to the next. If I flip a coin, the probability of getting a head is always 1/2. It does not change from trial to trial. The probability of finding a item being defective is going to be whatever the defect rate is of the entire production run. So in the sample that you've taken from that entire production run, the defect rate is going to be the same, trial to trial. And the trials are statistically independent. If I flip 9 heads in a row, what's the probability of flipping a head on the 10th row? It's still 1/2. If I've picked 8 defective products on my way to 15, what's the probability of picking the 9th one being defective? It's still whatever the defect rate is. So in a binomial distribution, we have n number of trials, and p is the probability of success of any single trial. So what we consider the probability of interest is considered a success. This is a little confusing when we do quality management because oftentimes we're counting failures and we use the success. We count a success as finding a failure, which is kind of weird, but that's the way it works. So if we're flipping coins, it's much more simple. N is the number of trial. We're going to flip a coin 10 times. P is the probability of success, success being defined as getting ahead, and it's 1/2. Now the thing, R is the number of successes we have out of the n trials. So R is always less than or equal to or n. We could have 0 successes all the way up to n successes. Those would be the values that R could take. Q is the 1 minus p probability. Remember, everything is either is a success or a failure. It's a head, it's a tail. It's a defective product, it's a good product. So if p is, if we're talking about a coin, the probability of getting a head is 1/2. 1 minus p or q is the probability of failure, also 1/2. If the probability of getting a defective is, like, let's say 2%, p is 2%, q is 1 minus 2% or 98%. So the probability density function for the binomial distribution is defined this way on these n, r, p, and q. So the probability of r successes in n trials is this kind of complicated formula. P to the r times q to the n minus r. And then we have to count how many ways we can get r out of n. So it's this n exclamation point doesn't mean n said with great emphasis, or n minus r said with great emphasis. N exclamation mark is read as n factorial, and it's n times n minus 1 times n minus 2. Well, that's maybe a little bit misleading, so let's put an exact number in there. 4 factorial. 4 times 3 times 2 times 1 equals 24. 5 factorial is 5. You add a 5 to this, so it's 5 times 4 factorial. It would be 120. 1 factorial is 1. 0 factorial is 1. And these are both by definition. So if we were to enumerate the probability density function for a coin toss, tossing a coin 5 times, the probability of getting a head is 0.5 or a half. The number of heads you can get are 0, 1, 2, 3, 4, or 5. And if we put all the numbers in here and calculate this out, here's the answers you would get. The probability of getting 0 heads is 0.03125. Probability of getting 1 head is 0.15625, etc. You'll see that it builds up to 31,250, and then it's symmetric because it's a 50-50 probability. The binomial distribution, if the probability is not 50-50, if p and q are not equal and equal to 50, the farther it gets away, the more skewed the distribution becomes. It doesn't have this same symmetry. It's only due to this case. And Excel, you would use a binomial distribution, as you'll see in the example that I present later in the video for homework. That makes you not have to do these calculations. So find the probability of 4 heads in 5 tosses. So that's 5 factorial over 4 factorial, 5 minus 4 factorial, 0.5 to the 4th power, 0.5 to the 5 minus 4, which is 1 power, and you get this number. If you do all of that calculation, you end up with 0.15625. If you were to graph this particular version of n equals 5 and p equals 0.5, you'll see the symmetry that we talked about. So here, MSA Electronics is experimenting with manufacture of a new transistor. Every hour, a random sample of 5 transistors is taken. The probability of 1 transistor being defective is 15. See how the p equals 0.15? That's the probability of success. Well, success is finding a defective. I always laugh about that. I'm sorry. So we're looking at what is the probability of finding 3, 4, or 5 defective? Well, we could use a formula to solve this problem, but using a table is easier. And if they use a table, they would calculate these numbers, binomial table at 0.05, 0.1, 0.15, and then if you find this PDF, probability of exactly 3, exactly 4, exactly 5, so 3, 4, or 5, which means we add these 3 numbers up. If we open up Excel, we could do the same thing. Where is Excel here? Should have had it open already. Okay, let's just move to this section of Excel right here. And so if I say P equals 0.15, how many trials did we have? I don't remember. 5. N equals 5. Then we have R, we have PDF, and I'll actually calculate the CDF as well here and explain that both. Let's make this bold. Let's make it that way. And we have 0, 1, 2, 3, 4, 5. And if I want to do this, I say it equals binom.dist. I use that. And it's numbers, trials, probability, 0 for PDF, 1 for CDF. Okay, so here I want to put the trial, which is B8, which is 0. And then I want to put, or the numbers, and then the trials is here. And then I put a comma, and then I put the probability of success of finding a defective. And then I want to put 0 for the PDF, and I say, there's my answer. And I'm going to probably want to put dollar signs before the C for the N value, and for the P value, I'm going to put dollar signs there. That locks in that cell. So if I move this down, I get this. And if I make it a few decimal places, let's make it 4 decimal places, we get the same answer as we get here. 0.0244, 0.0022, 0.001. And if I go back to my Excel, you see that's what we get. Now if I extend this over, it still maintained these two numbers, and it actually maintained the row number. So that's my cumulative distribution. And if I move this down, you see it, well, it stays the same, doesn't it? It shouldn't stay the same. It's not right because it's supposed to be the B number. There we go. Now if I do it, sorry about that. I get the same thing, but I want to change it all to, I'm really making a mess of this. Once you start making a mess when you're making a video, it stays a mess. If I make it 1, it becomes the CDF. There we go. It adds up to 1. So for 0, and again, I encourage you to make all your tables pretty so that you can copy paste them and put them into a PowerPoint. I always use the same format, so we can make it a little bit bigger so you can actually see it. And first, at 0, it's just equal to what it is at 0. This one, 0.83, is 0.44 plus what it is at 1. And here you see, down here, it's 835. So it always adds, when I go here, it takes the previous one and adds the 2 PDF value to it. So it's always the probability of 2 or less, 1 or less, 0 or less, 5 or less. 5 or less is the whole distribution, so it's 1. It's a cumulative distribution. If I was to graph these and let's see, what kind of chart do I want? Yes, let's do that. The CDF, you see, increases up to 1. The PDF decreases. It's not a symmetric distribution. So this is the binomial. And then we'll make this one if we do a normal. Okay. So, and then watch the video on how to solve, there's another video that explains that even more. So here we go. We find the three probabilities in a table by adding them together. There's an expected value here. The expected value in a binomial distribution is n times p. The variance is n times p minus 1, which is q. So the standard deviation is a square root of that. It's not going to be in any of your homework, but in case you ever need to know it, the mean is np. And then they talk about using Excel, but I just talked about using Excel. So you can look at it in the slides if you want. So now let's go to the normal distribution. The normal distribution has this PDF function. It's continuous. And it really looks kind of complicated here. It's got exponents. It's got exponents in the exponents. But it has two parameters. The mean, the standard deviation. The only reason that probability and statistics professionals use standard deviation is because the normal distribution is so important in the study of statistics and probability, and it is one of the parameters. Otherwise, as a measure of dispersion, it's not an intuitive measure. Range is a much better measure of dispersion. The mean, that makes sense. We know how to take the average of things. We know that it's a measure of central tendency and how it works. But the reason we use standard deviation is because of the normal distribution PDF. So these are the parameters. But look at, there's a pi. What is pi? Pi is the same thing it meant in elementary geometry. It's that non-repeating decimal, 3.141516, whatever, it keeps going on, doesn't repeat, and how you find the area and circumference of a circle. So that number is there. So that's a constant. This value e is what's called the natural logarithm. It's a number just like, it's almost as famous as pi. It's not repeating, but it's 2.781 blah, blah, blah. I don't know exactly. I can't recite very many decimal places of it. The only variable in here is x. That's the random variable. So this is the PDF. There's not a set formula for the CDF because it requires calculus to do it. It's a calculus problem and it's beyond the scope of this lecture. Yet people, without ever having taken calculus, use the normal distribution. So the normal distribution is symmetrical, with the midpoint being the mean. It's the shifting to mean does not change the shape of the distribution. The value on the x-axis are measured in the number of standard deviations away from the mean. As the standard deviation becomes larger, the curve flattens. As the standard deviation becomes smaller, the curve becomes steeper. The area underneath the curve is always 1. That's why it gets flatter or it gets steeper, depending on how big the standard deviation is. So here's 3 examples. Here's a normal distribution with a mean of 50 and some standard deviation. It's that bell-shaped curve. It doesn't go to the x-axis. It asymptotically approaches it. The PDF is never 0. It gets really, really close to 0. And at 5, 6, 7, 8, 10 decimal places, eventually it's 0 to those decimal places. So it's infinitesimal if you get more than like 10 sigma away from the mean. Same thing when you go negative away from the mean. But if I just shift the mean, I shift it to 40, but I shift it to 60, with the same standard deviation, the shape of the curve doesn't change. It just translates from right to left. On the other hand, if I keep the mean the same, but make the standard deviation bigger or smaller, here's smaller, here's bigger, the area under the curve always has to stay at 1. So with a smaller standard deviation, the curve has to go up higher to cover to get that area of 1. Or if I make a larger standard deviation, which means it's a wider distribution, it's going to get not as steep, so that I still get the area of 1 underneath the curve. The way the book teaches this is using tables. Well, tables is so 1974. Well, 1974 is when I took my first stat class. We didn't have computers. We didn't have Excel. I think we barely even had no graphic calculators, but scientific calculators were just barely coming on the scene. So we had to do everything by hand, and there was a table for a normal distribution with 0 and 1 in every stat book, every operations book in the world. So whatever your distribution was, whatever the mean and standard deviation was, you had to convert your data to the standard normal distribution by doing this transformation. If x was your random variable and x had a mean of mu, which is a Greek letter for representing the mean, and sigma for the standard deviation, you had to do this transformation on x to get to the z value, which is a standard normal distribution. It has a mean of 0 and a standard deviation of 1. So if you want to find, for example, if mu is 100, sigma is 15, we want to find the probability that x is less than 130. Okay? And when we do this, the cumulative distribution is the only thing we look at for, that's the only value we can get for a continuous distribution. It goes from minus infinity up to the value. So it's the area under this curve. Remember, the area under the curve is 1. So we want this blue shaded area. That will be the probability that x is less than or equal to 130 in this case. So they transform it to a standard normal distribution, and really the z value is then 2, and it translates this way, and then you look up in the table 2 and get 97725. If we go to Excel, what are we looking at here? We can make this bigger too. In this case, I want to say equals norm, and then I'm doing norm. If I want to do standard normal distribution, it's that one, excuse me. If I want to use this one, you put your x value in. What did we say our x value was? 130, comma. What's our mean? We said 100. What was the standard deviation? Standard deviation was 15, comma 15. And then is it cumulative or not? The only thing we can look at is cumulative, so we have to put 1. They say it's true or false, but 1 is true, 0 is false. Works. And we get 9772499. What did they get? 9772449 or 25. Again, do we need all these decimal places? Are we flying rocket ships to the moon? I don't think we need that many. So we can take it down to 3 or 4 decimal places. So you see this method of using this norm.dist in Excel is much easier than going to the system of looking things up on tables. Never do things come out this clear. The answer doesn't come out too very nicely. So here, Haynes builds 3 4-unit apartments called triplexes and quadruplexes. Total construction time follows a normal distribution. Triplexes, and that's what we're talking about here, is 100 days, and the sigma is 20 days. So the mean is 100 days with a standard deviation of 20. The contract calls for completion of 125 days, and late completion will incur a severe penalty. What is the probability of completing the triplex construction in less than 125 days, less than or equal to 125 days? Well, they do that z transformation, so now they get 125, and they go here and look at it and calculate it, and it comes out 0.8943, but we can do the same thing. So this is Hayes triplex construction, and what do we have? Mean was 100, and the standard deviation was 20. Standard deviation was 20. Now I can, using these two numbers, I can calculate anything I want. Probability of, let's say CDF, and we want 125. So, oops, this is the CDF. This is X, the random variable. So let's, again, left justify these. Let's make it bold. Let's make a blue tint. I think I got 3 maybe. I don't know how many I'm going to do here, but right now we'll just leave it that I'll box it in later. So here I go, equals norm.dist of X. There's my 125. Where's my mean? Right there. Where's my standard deviation? Right there. Is it cumulative? Yes. And if I say yes, I get my, let's take it down to 4 decimal places again. 0.8944, what did they get? 0.8944 or 0.89. So that's good. We got the same value they did. Now, I still want to do the same thing here. I want to put the dollar signs around the C's for the mean and the standard deviation so that I change these values. I can change it to whatever I want. Let's change it. If I put 100, which was the mean, and I put 75, which is there, and I don't know, I can put other numbers if I want. But if I do this, you expect the mean to be, the CDF to be 50%. And here it should be 10%. If I go the same amount from both sides, the cumulative distribution should add up to 1 if I do that, and those two do. If I had 8944 and 1056. So let's go back to here and see what else they're asking us to do. So what's the probability? What was the question here? What's the probability that they'll finish a job in less than 125 days and not incur a fine? It's about 10%. 10.6%. So 10% of the time they're going to be paying a big fine. The next thing is if they finish the job in less than 75 days, they get a bonus of 5,000. What is the probability they get a bonus? That's why I picked the 75, obviously, is a 10% chance they get a bonus. So 10% of the time, 10.56% of the time. If we were to do the probability of, this is the probability of not paying a fine, right? So a probability of, we can call it 1 minus the CDF, is equals 1 minus that. There is the probability of paying a fine. Now, I'm not doing what I preach. I'm not putting it in a text box and answering it in a full sentence. I would want you to do that. I'm doing this kind of quick and dirty. Okay, what's the probability of X being, I don't incur a fine and I don't incur a penalty. So now I want X to be between 75 and 125, right? Oops. Yeah, that's my X. There it is right there. Okay, so what's that probability? Well, that's going to be the same as the probability of less than 125 and less than 75. So if I look at here, there's my 125. I did this blue shaded area, and I subtract off this blue shaded area. So if I take this 125 cumulative density function and I subtract off this little bit, I'll get the in between 75 and 125, which is what I want to do. So it's going to be, this is going to be equal to that number minus that number, or 78%. And that's about all the kind of questions I'm going to ask you. If you want the tail, you have to do the 1 minus the CDF. To get the upper tail, the lower tail is in fact just the CDF. These are complementary probabilities. So if the probability here is 0.89435, here it's 10,565. And just like we did in our table, right? Here's the CDF, here's 1 minus CDF, and it tracks very nicely with what they did in the textbook. And if you go to the lower tail, that's it. If I want to get the upper part of the tail, I just do 1 minus that, and I could get that. So we have to complete, if we want to complete the probability of completing in 110 days, find the area between these two. We know the probability of completing in 125 days is that, and the probability of 110 days, we don't know what that is, but we just go down here and put 110 days if we wanted. And what do we get? So I get 0.69714. So if I want to get the probability of 110 less than X less than 125. Now in that case, it's going to be equal to 89.44 minus the lower one. And there's only a 20% chance of being in that day range. So it's pretty easy. 20% chance, you got the same thing we got. So we've already done this part and using Excel. So this is called the empirical rule. No matter what the mean and standard deviation is, 68% of the values fall between 1 and 2 1 standard deviation, plus or minus 1 standard deviation of the mean. 95.4% within 2, and 99.72% between 3. Why do I know it's 99.72, even though they didn't say it here? Plus or minus 3 standard deviations is a number we use in quality management all the time. And everybody that has done any kind of quality assurance work knows that plus or minus 3 standard deviations is 99.72% of the distribution. So you look at, here's what we're talking about. In between plus or minus 1 standard deviation, no matter what the mean is and what the standard deviation is, always 68%. Each tail then is about 16%. If I go to 95.4 for plus or minus 2 standard deviations, each tail is about 2.3%. And if I go to plus or minus 3 sigma and I get 99.72, the tails then are only about 0.15%. So we're going to stop there because we're not covering the F distribution. It's not fully a probability statistics course. So this is your drink from a fire hose of that. Thank you very much, and we'll talk to you soon.